Okay, thanks very much for coming along. So this is the first weekend of 4 weeks of the exemplar homes tour. So the idea is, hopefully everybody's got a map. The idea is we've got 7 homes throughout the city, and they're all exemplar homes, which basically means they're showing innovative new ideas to sort of demonstrate that there's a better way of building houses, and so model homes, if you like. And so they're all different construction methods. Some of them are zero energy and have a variety of different features. So these 2 homes here, they were originally designed as New Zealand's first 9-star homes. At the time, 8 was the highest. And then we worked out while we were building them that we could get to a perfect 10. So we basically had to do everything to get to that level. There's about 30 innovations in these homes that are not common in typical New Zealand homes. And both houses are 10 stars. So we finished the 2-storey house in August last year, and when it was launched, it got quite a bit of press, and we used that as a bit of a platform for launching the superhome movement. And the superhome movement is really about creating awareness and telling people that it's not too difficult and it's not too expensive to do a much better home than a normal building code home. So in New Zealand, 99% of homes are built to code minimum standard, which on the 10-star scale, home star scale, is 3 out of 10, and it's a very poor standard. So the superhome movement is an industry-led, not-for-profit group. The first aim is to educate the public, and then also professional development for the industry and the trade. So there's architects, builders, subbies, suppliers that are all participants in the superhome movement. So it's kind of a referral network, and you know that if you're dealing with one of those people that are participating in the superhome movement, then they know what they're doing, because you have to be invited to join the superhome movement and participate. And you have to be already doing good things or want to learn how to do better. So this house here, it's great that there's been a lot of interest in this home, and it's more than just about this home, it's about the whole movement, sort of creating some behavioural change. If you can stand anywhere other than there, we've got a camera there.
Oh, sorry.
We're recording. Thanks very much. Yeah. So first of all, the most important thing is to design for the sun, and you'd think it's pretty straightforward, but a lot of people don't get it right. So here, north is this way, so we've got minimal south-facing glass, we've got a lot more north-facing glass. And you can have too much, so if there's too much north-facing window, the house could overheat, or it could be too cold in summer if there's too much glass, because the windows really, I look at them like a hole in the wall, so that's the weak link, and it's 1/10 of the thermal value of the wall. So on the east side, we haven't got any overhang except for the entry where there's a bit of a canopy, more to keep the weather off. On the north side, we've got a recessed, our windows are recessed, and there's a balcony. So that gives us some shading. And then round on the west side, we've got a metre overhang for the roof. So you don't want your bedrooms getting overheating and it being too hot. You won't be able to get to sleep. And then on this side, we've got a carport, which in this situation, I'd see that as more than a carport. That's kind of a roofed outdoor living space if you back the car up, because that's where your afternoon sun is there too. So this north-facing wall, these black metal clad pieces here, that's actually a solar wall. So that's preheating the air that comes into the house. So there's a cavity there, and the air comes in at the bottom and goes in, is ducted into a heat recovery ventilation system at the top. So on 0 degrees frosty morning with just a little bit of sun on that wall, we can get 27 degrees pre-warmed air through into the energy recovery ventilation system. And that system is also keeping a really good air quality within the house, so it's extracting air from stale, moist air from the bathrooms, toilet, kitchen, delivering fresh air to the bedrooms and the living space, and it's very efficient. So that's
What about when it's too hot?
when it's too hot, there's actually a bypass, so there's a damper, shuts that off, and then it brings in cooler air from the south side of the building. Good question.
I've got one. What do you do on a cold, cloudy morning when you're not getting sun? Is there still enough warmth in the building?
Yeah, there's the house. I'll go through how the house is heated and how we can basically have no power bill. And yeah, so maybe what we'll do is we'll just have a Q&A at the end, because a lot of the questions might be answered along the way. And yeah. So, but actually the heating system is this, and how that integrates with the whole design of the building is the single biggest energy saving feature. So in this living space, we've got a new product from Jib, a sound attenuation Jib, so that basically absorbs the sound, so it's less reverberant, and it works really well when you've got hard flooring, otherwise it might be a bit noisy. And so that's what that room looked like before we put the pool table in there. It was a bit more space, and but we still managed to keep our seating over the other end, which was good. But it doesn't quite look like that, because that's one of those magical wide angle lenses that make it look twice as big as what it really is. So yeah, anyway, so that's the website. There is a website for this project, so there's probably too many things to talk about today, so you can go to the website. So these two houses were built at the same time. This one was finished a little earlier. We sort of pushed ahead with this one because there was a race on to be the first 10-star home, and somebody was trying to do one in the North Island, and so it was a bit like the block. We were working around the clock, and we bet them by 2 weeks, so my name will be mud up in wherever that was. Anyway, so the good thing was that it's created a bit of awareness, which is what we were trying to do with this project. Yeah, so that website, you'll see some of the ideas, some of the innovations, and there's also the Superhome website is a really good source of information too, because on the Superhome website, which we sort of briefly touched on, there's 2 sections. There's learn how, and then which has got like all the good things you need to do, and then know who. So, and it's a nationwide initiative. So you just click on whatever region, and you can see the people that are involved. So the first principle with how we've designed these houses is make them spatially aware, eliminate any waste space. So you'll notice there's no hallway, so we've just got the stairway dividing the living and the kitchen dining area. So we've replaced the ubiquitous island bench with a table. So we had acres of bench space around the outside, and then back in here we've got the, if you haven't already been in here, there's a kind of walk-in pantry, could be a scullery, and that basically eliminates the need for dining in the living space, so almost a whole nother room spaces, and that just gives us more living space. So so back in here, you probably had a look around, but normally the laundry, that's where we've got our humongous coffee machine, which uses more energy than anything else in the building. It's about 3.5 kilowatts. And then toilet and access to the carport out there. So even with that coffee machine, we're still getting a check for our power. And then back in here, this is, I call this Harry Potter's secret cupboard. So in here is the batteries. We've got saltwater batteries, first in New Zealand. We've got the solar control gear, and a bigger than normal special hot water cylinder, but we'll get to that later. So that links to the underfloor heating. So upstairs, it's fairly efficient too. So instead of what would normally be a hallway or a common space to circulate to the different rooms, we're thinking that could be used for an office, so we could have a desk in there. There's nothing there at the moment, there's just some seating, but so it's just a bigger than normal landing that we're going to give it a purpose. There's 2 smaller bedrooms, still big enough for double beds with built-in wardrobes. There's a larger bedroom. Normally there'd be wardrobes there, but we left the wardrobes out because we knew we were going to be using that as our office space. So that has an attached ensuite, which is quite a large ensuite for the LifeMark standards. So to be a 10-star home, you've also got to be 5-star LifeMark, which is about accessibility and adaptability and ease of use and things like that. And then there's a shared bathroom with a bathtub, which is also a good sized bathroom. So the other house next door, that's 118 square metres, and it has 3 bedrooms and 2 bathrooms. They're not quite as big, maybe 1.5 bathrooms. One's just a toilet and a shower. You're welcome to have a look at that house later if you haven't already. So this house here is 140 square metres, 70 above. So the main innovations are listed here, but that's not all of them. And so the thing is, I'll probably go into the slab, the walls and the windows in detail because they're the most important. So the thermal envelope of the building is by far the most important thing, and keeping the heat in. So we've got a fully insulated slab, it's a heated slab, and normally the edge of the slab is not heated in New Zealand, is not insulated, sorry, in New Zealand construction, and it's pretty much essential if you're heating the slab, because 80% of the heat is lost out the edge of the slab rather than through the bottom. So, and yeah, so we've got different type of wall framing. So I'll talk about that later too. We've got 18 solar panels on the roof, 4.1 kilowatts. We've got 4.5 kilowatts of battery storage. The house is more earthquake resistant. We've got more than double the code requirement for bracing because of how we've constructed the house. So it's unlikely to be damaged if there's a big earthquake. We've also got earthquake dampers, which are kind of like big shock absorbers. And then we're recycling the rainwater, and we're also treating the wastewater. We've got a grey water treatment system, and we're taking the water from the bathrooms, and then, well, first of all, there's an energy drain that takes the heat energy out of the wastewater, 39 degrees water that goes down the drain, and then it preheats with a copper coil, preheats the water that goes up to the shower mixer. And then we're filtering the water. There's a little shed out the back there with the equipment and a tank. And then that water gets added to the rainwater tank, which is a bigger tank, and then it gets plumbed back in to run the washing machine and the laundry tub and flush the toilets, and can also be used for irrigation. But in this case, our coffee machine is where the washing machine normally is. So that's why our coffee tastes so good. Actually, the grey water is perfectly fine. Yeah, it just tastes like normal water. I've drank it a few times out of the tub, and I'm still alive. So you can actually use it for the whole house. So there's obviously LED lighting. It's come a long way. It's cheaper and better. I really look at the LED lights like a skylight. They're transferring the sun's energy to another part of the house, but because it's free. So, all right. So the slab here, we've used a structural insulated panel, or SIPS panel. It's a permanent insulated formwork. So that's this piece here on the edge, and so you can use that, you can make a whole house out of that, but in this house we've just used it for the edge insulation and protection for the slab. So like I said before, that's where 80% of the heat is lost. We've also insulated under the footing, so that's not normally done. And this house here, there's an R value or thermal value of 3.36, so normally it's about 1. So pretty much everything in this house is triple code minimum requirement in terms of its insulation value, which is what it needs to be. So that's a photograph of it installed. So this piece of this insulation here, normally you wouldn't have that, you just see black polythene. So this is a raft or waffle slab, super slab. So TC2 site, so we needed an enhanced foundation. So these pods here, they're really there just to save money on concrete and form the beams or the ribs in the floor to make it stronger if there's an earthquake. So people kind of get the misperception that, you know, there's lots of polystyrene there, it must be good insulation, but that actually does practically nothing for the insulation. The insulation, the important part is the edge. So, you know, research shows that if you increase the normal 50mm poly that goes under the slab to 250 mils, it does very little. So the important part is the edge, because the air temperature outside could be -0. The ground temperature under the house is still going to be 8 or 10 degrees. It's more constant. So the heat will just find its way to the weakest link. So that's it with the water heating in the floor. And really essential that you've got an insulated edge. 99% of homes don't have it. It's not required. There's another way of doing it. So Max Raft is another product. There's some brochures on the bench there about Max Raft. So that's an integrated solution for an insulated floor, fully insulated floor with an insulated edge. And actually Max Raft have a brilliant photo. I should probably include it in this, but there's a house they photographed down in central Otago. Frosty morning, ground covered in ice, and then there's a strip about 1 metre wide around the edge of the house where it's thawed. So it was just showing that they're actually heating the garden with their underfloor heating system. Be a good place to plant the tomatoes. So yeah, good idea not to do that. So this is a thermal image that we took. This is just the lounge window through there. And then this is outside, so this is outside there. So basically this is 12 degrees to 21 degrees, that scale. So the floor's 20 degrees, the wall's 17 degrees, the window's 15 degrees. You can just make out the stripes there where the studs are, because that's a thermal bridge where the timber is. It's less insulation than the timber is a poorer insulator than the insulation material, obviously. So this one here, just to confuse things, it's the same colour but a different scale. So that's -1 to 3. So the outside wall is -1. So this was on a frosty morning. The timber cladding there, that stuff there, that's -1. The aluminium is around about 0. Sorry, the windows are around about 0. So it's working brilliantly. We're not leaking a lot of heat. A normal house would be a lot different. For example, the window frames, if they're aluminium window frames, there wouldn't be much difference in temperature inside to out, and that's why you get condensation. So here you can see the window frames are hotter, foundation slightly hotter, but it's still between sort of 0 and 2 degrees, so it's still minimal heat loss. So that's great. So just before I get onto the walls, the foundation, the reason we've got no power bill is basically because we've done the foundation like this and the heating system. So our hot water cylinder in here is heated via a heat pump outside, which is a tiny little heat pump, 1.1 kilowatt input, 4 kilowatt output. So we're taking 1 kilowatt of solar power from the panels on the roof. We're converting that into 4 kilowatts of hot water, and we're putting it into this larger than normal hot water cylinder. And that hot water cylinder has a special new type of heat exchanger coil which is really efficient. So that takes the heat out of the cylinder, and this little pump, red pump on the bottom here, just circulates the water through the floor if it's needed. So it's all thermostatically controlled. We don't have to think about it, it just does it. So I really see this as our battery. Water is a really good storage medium for energy, and the concrete floor as our second battery, because concrete, the thermal mass of the concrete is a good storage medium. And then our batteries, our saltwater batteries in there, which are wonderful because there's no harmful chemicals, no heavy metals, very environmentally sound. They're just really storing the electricity for running things at night, like the fridge and the lighting and whatever we plug in. So in any home, 70% of the energy required is actually thermal energy. So heating your water, heating your house, your space. 30% of the energy is for what you plug in, your electrical stuff. So the heating system only works during the day. So because the house is so good, because we've got thicker walls, we've got the really well insulated floor, we've got much better windows, and you know, everything combines to make our heating requirements less than 40% of what it would normally be. So that's why we can just heat the water while we're generating power. There's actually a daylight sensor, so it just doesn't turn on at night, doesn't need to, and that makes us really energy efficient. So you come in here in the morning and it could be 0 degrees outside, you get hit with a wall of 20 degrees air, and you know, you feel smug because you know that's not costing anything. It's a bit like the people who run around in their electric cars knowing that they don't have to fill it up with gas. Yeah. And that really turns the equation on its head. If you can have no car bill for your house, but also have no fuel bill for your car, which is what they're doing next door with their electric car, powering the car from the house. So that's interesting. So, the other thing with just with this system here, the requirement for the heating system is basically smaller and cheaper because we've insulated the floor properly. So we don't need as much plant, and basically the extra cost in insulating the floor we save by having a smaller heating system. And then you've just got the ongoing better cost of, lower cost of ownership, lower running cost as a bonus. So the timber, it's a timber frame house. So this isn't, none of this is rocket science. A lot of this is existing technology just packaged together, just designed to work cohesively a bit better. So, you know, underfloor heating's not new, solar's new, but how it's all put together in this house is new. So this house here has timber framing, but it's a new type of timber framing, and it was, I think, one of the first houses to have this type of timber framing. This system's just being released to the market now, so we were early adopters of it. So that there is the traditional way of doing timber framing. You've got 3 studs in the corners, 3 studs where the wall junctions are. This is the new way of doing it. You don't need all those studs, so less timber, more insulation. So the red is the amount of insulation you can fit in the wall, and it's actually stronger. So there's metal angles, you can't see it in this photo here, but there's lightweight metal angles to join the wall. There's a lot of advantages. So the dwangs are vertical, so the insulation can run continuously without having gaps in the insulation. And the plumbing and electrical, you don't need to drill holes through the dwangs, because the dwangs in a normal house would be horizontal and you have to drill through them. And in this house, we sort of took it a stage further. We actually removed the dwangs completely, because there's nothing in the code that says you have to have dwangs, and they don't do much structurally. So it's just one of these things, we've always done it that way. So I actually went around and removed the dwangs, and then the walls are thicker, so they're 140, and they're LVL, which is laminated veneer lumber, which is stronger and straighter. Builders love it. They don't have to straighten the walls and that. So that idea there, this will be the new normal way of doing timber framing going forward, and it's cheaper. So that's a bit of a no-brainer. You know, if you can do something that's better insulation, stronger, and it's also cheaper. And I don't know if this is going to work, but there's a little video there. It may work. It's probably can't use this, but I can probably do it over here. Yeah, so that's just showing an animation of what I was just talking about. So, you know, normally at the corners there's no insulation, you can just get the cold coming through there. The other thing with this is there's a better finish too, because you're screwing into metal angles. So there you can see the studs coming out, insulation going in. So if you screw jib into metal, there's less chance of popping of the fixings. So you're not going to get that problem. So this is the best way to do timber framing. The next step on from this would be not timber framing at all, a panel system, and there's a number of panel systems. You know, I mentioned this one here, there's other ones too. So we'll see different building methodologies coming through in the future, and there'll be less and less traditional building. So that's that, and there's just this crazy guy removing dwangs. Didn't take very long. And I also put the insulation in myself too, because in New Zealand houses, the research shows that over 75% of homes, the insulation is installed faulty in New Zealand. So you could spec R4 insulation, and by the time it's installed with just little gaps or just not done properly, it could be R2 in practice. So we're trying to have no power bill, so I thought I'd better do the insulation myself to make sure it's done properly. So the windows, this is a drawing, sorry, you know, there's a lot of technical stuff and drawings, but I'm looking at it every day, so I can see exactly what this is. But this is your weatherboards outside, your cladding, and this is your jib on the inside. So basically this is the cold side of the wall. There's a drainage and ventilation cavity there, typical in New Zealand homes, and then the red is your insulated part of the wall, the warm part of the wall where the insulation is. So in every house, pretty much, 99% of homes in New Zealand, the windows are installed like this, with the windows flush, overlapping the cladding in the cold cavity. And that's because this is the building code detail, and this is what people are told to do. And so this line here, in this drawing, there's building wrap, or building paper. In this house we've used a rigid air barrier, which is another thing that makes the house warmer and stronger, so it's more airtight and it's better braced with a rigid air barrier. But that line there is where you're going to get condensation, because where the cold meets the warm, that's just where the condensation is going to occur. And guess what? That's just where the glass is, so that's why we get condensation on our windows, because that's right where our glass is. And this is an aluminium window. We did it differently in this house. We, first of all, got thicker walls, but we've installed the window in the warm part of the wall. And now we're even installing it further back in the wall. So never going to be any condensation. It's a PVC window, PVC framed window, and it's got high performance insulated glazing units, which I'll talk about. But so much better window, but also installed recessed, so it's going to work much better. So if you look at this window here, we just go back over here. If you look closely at an aluminium window, there's a drainage channel on the bottom, the little graveyard for dead flies and for mold. And so they know that that window is going to have condensation. They've designed their product knowing that it's going to fail, and and they drill holes through the aluminium window frames so that condensation can drain outside. So you put a lot of effort and thought into doing a warm, energy efficient house, and you've still got holes drilled through your aluminium window frames to the cold air outside. So that's bonkers. And then there's a big aluminium heat sink, or cold sink in this case, which is here, to support that window, because otherwise it's hanging in mid-air and there's nothing to support the weight of the window. So here, our window is supported on the structural frame because it's recessed into the wall. So what are the windows? So I talked earlier about the windows and the importance of the windows, you know, the orientation of the house and the proportions, location of the windows. It is really, really important to try and do a better job with the windows. If you're going to do anything better in your house, the windows. Because, like I said, they're a hole in the wall, they're the weakest link. And here, our windows are roughly 3 times as good as a double glazed aluminium window. So we're basically leaking a third of the heat. And, you know, our walls are thicker. It's easy to comprehend. You know, if your walls are twice as thick, you're losing half the heat, sort of thing. So, double glazing. There's double glazing and there's double glazing. So, if people say, "Yep, she'll be right, she's double glazed," real estate people, builders, you know, they don't know what they're talking about, because these are double glazed windows, but they're 3 times as good. A really key thing is the spacer that goes between the 2 pieces of glass. So if we look at this here, there's then all the major glazing companies give you a piece of metal that goes between the glass. So you've got to ask for a piece of plastic. Crazy, but that's the way it is in New Zealand. So that's called a Thermex spacer, and that makes a big difference. So the next thing is PVC frame. We already talked about that. Anything other than aluminium. So timber is good, but it's more expensive. Aluminium is not used very much overseas. It's seen as a very poor performing product for windows. You know, it works great if you've got a solar wall, like that black wall out there, to warm out air, but it also is because it's a good conductor, it lets the cold through the window frame. So the next big thing might be fiberglass windows, but there's a big move towards PVC in this country at the moment, because we basically, it's been a real niche. We haven't done much with PVC, whereas the rest of the world, about 80% of the windows are PVC. And it's an urban myth that they're going to break down in our UV too. So, you know, it's a very different type of PVC than the old brittle rainwater gutters. Low E is the biggest performance gain. So 30% increase in performance by using low E, which is basically a coating on the inside of the double glazing unit. There's 3 levels of low E, so you need to ask for low E XL, which this house has, so that's the best one. Argon filled, so that's just a gas that's heavier than air. It's cheap. It's only 10% increase in performance, but we do it because it's not difficult. So a typical PVC window, good PVC window is 0.53 value. An aluminium double glazed window is 0.26, so it's already double. And the glazing, the NK windows who did these windows told me these windows are 0.77. And I think they're much better than that because we've actually installed them properly and recessed them into the wall. So you can see that there, they're recessed. There's your cavity. So, and the green material there is your rigid air barrier, which makes the house more airtight. So thermal mass, I touched on that. Solar, we've got our solar panels. Another thing that's really important in any home is air tightness, and that's something that is absent from the New Zealand Building Code. There's nothing about air tightness. It's kind of the skeleton in the closet in New Zealand building. We don't think about it. In other countries, Europe, European countries and North America, there's actually standards for air tightness. To get a building consent, you have to reach a certain level of air tightness between 1.5 and 3 air changes, I think, in most countries. Passive house standard is less than 1, which is a European standard. So 0.6. So, but New Zealand homes are 8 to 10 air changes per hour. So if you think about air tightness, 10 air changes per hour as opposed to say 1, that's 10 times the amount of air which is escaping through the walls, through the gaps, and that's 10 times the amount of air that you've got to heat. But that's not the biggest problem. That's going to make the house, if it's airtight, it'll be 10 times as energy efficient. But the biggest problem is moisture in the walls. So if you're getting condensation in the walls, if you haven't done a good job with your thermal envelope, then that interstitial condensation can create an environment where you can get black mold, and that's common, and in new houses too. So relatively new houses. So in New Zealand we've got a real problem. We've got 1 million or so unhealthy existing homes, and we're adding to it with unhealthy new homes. So I think the real problem is not the cost of power, it's our health issues. And you might have seen in the news lately, Andrew Little and the Labour Party are trying to put through a bill to change that, and I think it's a really important thing, because our building code isn't going to change, and this is why we're doing the super home movement, to make people aware of these things. So building code is basically 3 stars, and we know that because we're Homestar assessors, and Auckland has made moves to implement 6 as a minimum standard. So in Auckland you've got to build to 6 Homestar in special housing areas or multi-unit developments, not all houses. Christchurch tried to introduce that to the replacement district plan, and it didn't make it. So we're still back here on 3 stars in Christchurch, and some of the reasons it didn't make it is the group home building companies complained, even some architects complained who don't understand that it isn't too expensive to do much better, and the government asked for it to be removed from the replacement district plan. So yeah, shame on them. This area here is where we should be. Super home movement is, you're not a super home unless you're 6 or above. So we're commonly around 8, 10. It's a stretched target. It's probably a bit too aspirational and too expensive for most people. You don't need to do 10. You can have an 8-star house which has no power bill, just without some more of the bells and whistles like batteries and grey water or whatever it is. So, what are the key issues? I really think health is a big issue. Which one of these people has the most effect on public health? It's not this guy here. It's not the doctor. And I couldn't find a Lego architect, so I photoshopped his black turtleneck and put a pencil on him. The builder, most 90% of homes are just built by building companies. They don't get designed by architects. And so if we all lived in healthy homes, there'd be 30% less hospital admissions, there'd be less deaths. The most affected are the very young and elderly people, because they spend most of the time in their house and most susceptible. And productivity, there'd be less days off work, so we'd be happier, healthier, more disposable income. So this is widely accepted research, so this isn't just me saying this. We have the highest asthma rate in the world in New Zealand, and it's because of our crappy housing. So most people say that's all good, but what does it cost? This is probably 2 or 3 years out of date, but this is the ratio. If you spend 0 extra money on your house and you have a building code standard house, your power bill might be that. If you get to 6, Auckland identified 6 as a good standard, so 2.2% more, your power bill will be roughly half what it would normally be. And Housing New Zealand, Christchurch City Council, their social housing, they have 6 stars as a minimum standard. So if they can do it, anybody can, because they're really affordable houses. So this house here is one that we did, the predecessor to this 10-star home, and that's actually just over the down Ward Street, which is off the south side of Church Square over here, and that didn't have all, it had some of the good things that are in this house, but not quite as good. So it had the insulated edge to the foundation, it had the good windows, had thicker walls. And we collected the power bill for the 12 months of the year through the seasons, and that had a $580 power bill for the year. So they got a check for their power in the summer, and they got they pay for their power in the winter. They put 2 kilowatts of solar panels on that house. We specified 4, so we worked out if they put the full 4 kilowatts on there, their power bill, that $580 a year power bill would be completely wiped out. So that would be a zero energy house, or an energy positive house. It's a simple house, and it's not too expensive. It would be more today, so that's 2012, so there'll be some inflation on that. So this is a cross section through this house before we decided to get rid of the island bench. And then this is illustrating, this is a static image, but this we want to develop into an interactive infographic, or I'm calling it a dashboard, so you can click on whatever rating, you can see what good things you need to do to achieve that, insulated edge, yeah, and these things. So, and it'll tell you the energy performance, it'll tell you what your power bill will be, it'll tell you what the cost to build is, and what the end value of the house is. So that'll vary depending, the property value will vary depending on where it is, whether it's in Addington or Pendleton, or size and value of the property. But there's a mortgage calculator here. So if you take what you normally spend on your power bill, put it on your mortgage, that might reduce it from, say, 25-year term to 15-year term. It could save you $100,000 plus in interest, depending on the value of the property. So it makes complete sense financially, and in terms of health benefits, just comfort. It's just much more comfortable. And then what's the psychic benefit of, psychological benefit of having a warm, comfortable, healthy house that you enjoy coming home to and having people over to dinner? You just feel better about it. So if you're going to remember anything today, just remember code doesn't equal quality. Forget about the building code. So why are we not doing greenhouses in New Zealand? Less than 3% of homes are designed to be energy efficient. It's the most dangerous phrase in the world. We've always done it this way. We haven't moved on. So we're probably about 15 years behind a lot of other countries. So we need to, I say, the building code is, that's our sort of protection that's put there by the government. So legally, you're not allowed to do worse than 3 stars. So that's the worst possible house that you're legally allowed to build in New Zealand, 3 stars. So, and that's what we target. So the group home building companies, they're sales driven, they're not design driven. So they're all about cheap, cheap, cheap. So get the sale. They don't tell the customer what they need to know about any of the things I've been talking about, because they fear that might make it more expensive and they might go down the road to somebody else. So we need to be more design focused, less. We've got this obsession in New Zealand with how big a house can I have for how cheap a square metre rate, which is really propagated by the home building companies. So we need to start to realise that not all houses are equal, and you've got to start to look at the details. So I really think that you need to consider the cost of ownership, the return on investment, and those things are just not considered. So we're basically largely financially illiterate when it comes to home ownership and home building in New Zealand, because we're not thinking about the full picture. We think about our cars more. So 2 prices to every car. There's the window price, there's the annual running cost. By law, that actually has to be displayed in the side window of a new car on the lot. And he could do an ad on TV about that. So this one here, we know that price there. This one here, nobody thinks about it. So even with an existing house, you should ask the real estate agent, please, can I see a copy of the power bill? I want to know how much it's going to cost me, because the number is much bigger than the car, but we don't think about it. So with our houses, we can pretty much tell you what your power bill will be based on the design of your house with the ArchiCAD software that we're using. So just finally, size is important. So we build the second biggest houses in the world. So the rest of the world, they're trending downwards, house sizes. We're still one of the few countries that's trending upwards. And we build bigger houses than in America. So we're off the chart here, and we've got the unenviable statistic of being the second most expensive place in the world to build a house. Netherlands is number 1, but they're probably building 8, 9, 10-star houses. We're building 3-star houses. So we're getting a bad deal all round, and it doesn't need to be that way. So that's why we've created the super home movement, so that the public can get the right information. It's not just about energy. Earthquake resistance is important, and also design. So just having a home that actually has design integrity, has a nice feel about it, and you can feel proud of. So there's no point in having a 10-star home with no power bill if it's going to be the ugliest house on the street, or if it's going to be destroyed after an earthquake. And the building industry uses 40% of the world's resources, and heating houses uses far more energy than any other sector. So if we can do a better job of we need to do a better job of our houses. So otherwise, instead of 1 or 2 degrees global warming, we might have 5 degrees, and it could be catastrophic. So I think we need to make all houses energy positive, and it's not rocket science. Thanks very much.